Instead, what we're going to do right now is nerve stimulation lab. And this is kind of thinking about the pre-lab, thinking about what is this lab about? How do you actually write your objective and hypothesis? Which once it's done is just going to be a few sentences, but it's worth spending some time talking about what those sentences should be. So nerve stimulation lab, that's the one on next Tuesday. I need to introduce it. So things to a little background. And we talked about the sensory part of the nervous system. You know, the only way that you can actually have information coming into your brain, though, is along axons going from neurons, which means it's all these electrical signals. But a lot of the stuff we actually want to notice is not electrical. It's like light, or it's pressure or touch, or it's the presence of sugar on my tongue that I detect as sweet. So the actual stimulus, the thing that I actually want to detect, often is not an electrical signal. And in order to actually send information about that to my brain, though, it has to be converted into an electrical signal. So that idea is called sensory transduction. Sensory transduction, it's converting the stimulus, whatever it is. Maybe it's light, maybe it's pressure, whatever, you know, into some electrical signal for the nervous system to understand. Right? Your eyes and the retina convert light into action potentials that go down the optic nerve, which then you can interpret as vision in your brain. My voice right now is vibrating your eardrum. It's just physical movement that is being converted into electrical signals by your inner ear that then become action potentials down the auditory nerve that your brain can interpret in the auditory cortex. So we'll talk about this in more detail, but the basic idea is going to be at the core of all of the sensory neuroscience. This idea that any kind of stimulus that you're interested in, you typically need some kind of a receptor that will convert it into some electrical signal. So that's the first part of this. In order, like for touch, you have little touch receptors in your skin that convert the physical bending of your skin into an electrical signal, which goes up towards your brain. Here's you. Here's your brain, spinal cord. Maybe here's your finger with some little receptor. There's some little touch receptor in your finger that converts physical bending of your skin on your finger into an electrical signal, which then goes through a sensory nerve. An axon goes up spinal cord into your somatosensory cortex, ultimately, that post-central gyrus. And when there's when there's activity there in that post-central gyrus, then you have this experience that you are touching something with your finger. We had this idea of label-lined coding. Because this little part of the cortex is associated with that finger. So if there's activity here, then you assume that you must have had activation at the receptor on that finger. That's why they say labeled line, because if I just went in with an electrode and just stimulated that part of the brain, you'd still feel like someone's touching your finger. Or in the case of our lab, if I took some electrode and just kind of put some electric current across here and created a depolarization that started an action potential, even if nobody ever touched your finger, you would still have had the experience of some little tweak touching your finger. Right, so that, in fact, that in this lab, we are going to use a gentle electrical stimulation across the skin to basically depolarize these sensory receptors and send messages up your sensory neurons, even though you're not actually activating the actual receptor itself, through its normal modality. Normally you operate a touch receptor by touching it, but we are going to use an electrical current through the skin that will depolarize the axon and generate an action potential. So this is kind of the background. Other things we need to know. Sensory threshold. All right, so there's some stimulus, which is just something. Maybe it's touch or sound or whatever. There's some receptor that can notice this and creates an electrical signal, and it goes up to your brain. And at some point, you're like, oh, I'm noticing something. I have some perception. Oops, let me write that better. So you have some conscious subjective experience related to that stimulus. However, depending on the situation, you could have a stimulus and maybe this receptor is not sensitive enough, or whatever downstream isn't sensitive enough. Think about, you can have maybe the music is on, but it's so low you can't even hear it. You have to make sure you turn up the volume enough that you actually hear it. So there could still be a stimulus. There could be like really, really quiet music. Maybe like some other kind of animal could hear it, but not you. A cat could probably hear it. Frequencies as well. Like you can have, like cats can hear stuff up in 50, 60 kilohertz. To us, it would be dead silent. So just because you have a stimulus doesn't mean that you have a conscious experience of it. Sensory threshold. What is the minimum magnitude to just barely notice? The minimum magnitude of the stimulus. So if we're talking about sound, it's take the volume from when you don't hear anything, make it a little louder, a little louder. Finally, what's the minimum volume that you just barely notice it? That would be like the sensory threshold for, like, the volume of, of the sound. Or maybe it's pressure. What is the lightest touch that you just barely notice there's something touching you? That would be the threshold, that whatever that pressure is that you just barely tell that it's there versus not there. Light. What is the dimmest light where it's clear that it's not just pure darkness? That would be like a sensory threshold for, like, kind of, light intensity, where you just barely notice that there's something there versus nothing. So does this kind of make sense, this idea of sensory threshold? You're taking the stimulus and you kind of crank it up, but till you just barely notice it. So this is going to be our dependent variable for our lab in this one. We're going to be looking at sensory thresholds. And we got 5 minutes. This is going to work. The basic way is going to look like this. Here's the person. Here's like their finger, let's say. So they have their receptors and all the neurons that go in for touch for their finger. We're going to use a current source. And we're going to put it across the skin of the finger. Maybe I should put the finger the other way, actually. Back. I know what I want to do. There we go. So we have this electrical current that is going to flow through your tissue here. Electrical current is measured in milliamps. An ampere is the core unit. Milliamps are a measure of electrical current. The more milliamps, the more electrical current charge is flowing from one to the other electrode. You know, as you have more and more current flowing through your skin here, at some point you're going to depolarize things enough that it's going to create an action potential, which is going to go up to your brain and you're going to feel something. Right? If this current source is too low, then it's not going to sufficiently excite your sensory neurons in here, and you're not going to notice anything. But if it gets high enough, you will have enough of a change that you depolarize enough of these little axons that you're sending a message up to your sensory cortex that you notice as I felt something. So the threshold here, minimum current, you know, that the subject barely feels. So basically, we are going to take this system and we're going to crank the current. Start low to where you don't feel anything. Make it a little bigger. Did you feel that? No, I didn't. Make it a little bigger. Let's say now it's at 2 milliamps. Did you feel that? Nope. Make it 4 milliamps. Did you feel that? Nope, still didn't feel anything. Make it 6 milliamps. Did you feel that? Nope, still didn't feel anything. Here's 8 milliamps. Ooh, I felt something. You know, that value where you just barely felt it, that would be the threshold, right? If you go below the threshold, you don't feel it anymore. If you're above the threshold, then you're in the zone where you're feeling things fine. Does that make sense, what we mean by this sensory threshold? So this is going to be the dependent variable. Notice that to actually measure the dependent variable is going to be a process, kind of like the same way with the enzyme lab. You can't just measure it and get it as a one-shot deal. You have to measure at some current. Did you feel that? Nope. All right, let's change it. Let's go up to the next one. Do you feel that? Nope. All right, let's change it. Do you feel that one? Nope. Let's measure this. Oh, I felt that one. That's the number I'm going to write down for my threshold. But it wasn't one step. It was multiple steps to actually get that threshold. I have to do a staircase to get up to it. Right? If I did 2 milliamps and I felt it already, I'm too high. I got to go lower and start lower to where I can't feel it and come up to where I just barely feel it. So does that make sense? All right, so this is going to be the dependent variable. Our independent variables, we're going to vary two things. We're going to look on body location. We're going to look both on the finger and we're going to look on the back of the leg. It just means we're going to do the exact same thing. We're going to put the electrodes on somebody's finger and find the threshold, our dependent variable. We're going to put the electrodes on the back of somebody's calf and do that same staircase and find the threshold. Where would you expect a greater threshold or less of a threshold? How would you expect the threshold to vary with body location? I mean, that would be like my objective, right? My objective is a question. How does body location affect the sensory threshold?
I would expect the finger to have a lower threshold.
And why is that?
There are more senses in your finger.
Yeah, so
Sense receptors.
right, if you think about your finger, you have way more little, part of the reason your fingers are so sensitive, there's a lot more little receptors and nerves heading up to your cortex from your fingertip as opposed to the back of your calf. If you've been in Bio 110, you probably found, we'll find in our own class, you can detect things that are a millimeter apart on your fingertips. You don't even know if things are an inch apart on the back of your calf. So it's going to be a lot easier to bring this denser receptor array up above threshold than it would be if there was very few receptors around. So that's one of our things. We have independent variable body location, and again, just kind of the density of receptors is going to probably be a good indication of having, like, if very dense array, you probably need a lot less stimulus. It means to be a lower threshold. The other thing is going to be frequency. So independent variable 2. And but we're getting independent. I'm going to talk fast. Is going to be frequency of the stimulus. So we're going to have this current going into the finger. And we can just have a single pulse. The current is just a single pulse, and that's it. That's no frequency. There is no frequency. Or I can do pulsing. You know, I could do 1 every second. That would be 1 hertz. Hertz means per second. I can have 2 hertz. Twice as many, 2 per second. If I'm doing, I should probably do it. That's just 1 clap. There's nothing, hertz don't make sense there because there's no frequency. It just happened once and stopped. 1 hertz would be 1 per second. If I wanted to do 2 hertz, I'd have to do 2 claps per second. That would be 2 hertz. If I was going to do like 4 hertz, it would be 4 per second. It just keeps going and going at that many per second. So that is what we mean by hertz, by the frequency. And given that we have our finger and we have this electrical current going through here, what do you think is going to be a relationship between frequency and threshold?
The greater the frequency, the lower the threshold.
And why is that?
Because you would have the membrane voltage would not be able to repolarize as much. It would stay closer to depolarization, stay closer to threshold.
That's exactly it. So it's something we call temporal summation, right? Let's say I have some threshold of whatever. This could be in lots of just excitable cells. There's some threshold, and it takes a certain hit, a certain amount of excitation to get the membrane over threshold where it goes. But if I do a bunch of little ones, they can start kind of stacking. If you have the next one, temporal means in time. Like if I hit it once, it goes. If I hit it small, it might not go. But if I hit a bunch of very small ones right after each other, it kind of builds and will hit threshold. I'm not describing this that well. Again, let's say I have a big stimulus and it's enough to get me over threshold and something happens. But a little one on its own doesn't make it happen. But if I do the little ones in quick succession, then the membrane doesn't have a chance to fall all the way back down, and these start dogpiling, and they actually hit threshold as long as they're coming up behind each other fast enough so they kind of layer on top of each other and have a cumulative effect. That's called temporal summation. You keep exciting the same space, but you excite it in quick succession, and then you get an additive effect. So even if you have a stimulus that on its own would not have been enough to take you up the threshold, if you do that same smaller stimulus in quick succession, again, they kind of dogpile and you can get the threshold. So, and then we get, what John was saying. You don't need as high of an actual stimulus as long as they had a high frequency, because we'll still hit threshold because of this temporal summation effect. Does that make sense? Mm-hmm. So in your objective, remember you independent variable, there's two of them. There's body location and two, there's the frequency of the stimulus. And dependent variable is just going to be the threshold. So in some ways, there's like two questions. What is the effect of body location on the threshold? What is the effect of the frequency of the stimulus on the threshold? So are there any questions? I know I kind of went over a little bit there. And I have a thing on the web, I think, where I talk about that from like last semester as well. So you can look on the module and I go over this again. So, or actually looks like Tina does. So both of us. So anyway, I would say at least get a basic idea. Once we do the lab itself, I'll go more into detail, more things that we'll have to think about, ways to think about interpreting it. But I would like people coming in on Tuesday to understand at least the main point of what are we doing? What is the threshold? And then, okay, how is the threshold different on the finger versus the cap? Body location. How is it different as we change the frequency, start like getting the stimulus in quick succession versus just a single pulse? Or maybe in super fast succession versus kind of a slower frequency. So